In last lecture, we have to see the simple pendulum. In this simple pendulum, we have to calculate the value for the acceleration. That is, we have to get the relation between acceleration and displacement. Then we have to find out the value for the period of simple pendulum. That is, t is equal to 2 pi in the root L upon G. From this equation, we have to see some conclusion, that is, period of simple pendulum is directly proportional to the square root of the length. Then this period of oscillation is inversely proportional to the acceleration due to gravity. The period of simple pendulum does not depend upon mass, and this period of simple pendulum does not depend on its amplitude. And these conclusions are also called as laws of simple pendulum. In the today's lecture, we have to see the second pendulum. Pendulum whose period is 2 seconds is called as a second pendulum. That is, we have to get the formula for period of simple pendulum. T is equal to 2 pi in the root L upon G. Here we have to substitute the value for period of simple pendulum, that is a 2 seconds. We have to substitute in this value. In this equation, we have to get 2 is equal to 2 pi in the root L upon G. These two cancel each other. Then we have to get the value 1 is equal to pi in the root capital L upon G. Squaring on both the sides, we have to get the value 1 is equal to pi square L upon G. From this equation, we have to calculate the value for this length of simple pendulum, and we have to get the equation. Hence, L is equal to this term, that is G term, we have to take on this side, and this pi square also taken on the left side. We have to get the value, that is length of simple pendulum, which is equal to G upon pi square. From this equation, we have to calculate the length of the simple pendulum. Means, when we have to know the value of the acceleration due to gravity, we have to calculate the length of simple pendulum, S.H.M, and its differential equation. In this figure, we have to see that a metallic disc which is attached centrally to a thin wire. This thin wire may be the perfectly nylon or a metallic wire hanging from a rigid support. If this disc is slightly twisted about the axis, means when this disc is, when we have to twist it about the axis along the wire and released, it performs clockwise as well as anti-clockwise sense. Such oscillations are called as a angular oscillation or a torsional oscillation. The motion is governed by the restoring force that is this force. In case of the angular momentum, we have to know as it is a torque. That is, this motion is governed by the restoring torque in the wire, which is always opposed to the angular displacement. If its magnitude happens to be proportional to the corresponding angular displacement, we can call the motion is said to be an angular S.H.M. Means काय सांगितलं, when this metallic disc is we have to twist it and release it, म्हणजे आपण त्याला काय केलं, ट्विस्ट केलं आणि सोडून दिली, तर त्या ठिकाणी काय होणार आहे, त्याचे जे मॅग्निट्यूड्स होणार आहेत, ते मॅग्निट्यूड म्हणजेच आपला रिस्टोरिंग टॉर्क जो आहे, तो रिस्टोरिंग टॉर्क कुणाला त्या ठिकाणी अपोज करणार आहे किंवा प्रोपोर्शनल कुणाला असणार आहे, तर त्याची जी अँग्युलर डिस्प्लेसमेंट असणार आहे त्याला तो प्रोपोर्शनल असणार आहे. आणि म्हणून सांगितलंय तो रिस्टोरिंग टॉर्क आहे, तो रिस्टोरिंग टॉर्क वी हॅव टू डिनोटेड बाय द लेटर टो. अँग्युलर डिस्प्लेसमेंट विच इज डिनोटेड बाय द लेटर थीटा. मग काय सांगितलं आपण, when we have to release the metallic disc, when we have to release the metallic disc, तो metallic disc रिलीज केल्यानंतर काय होणार आहे, तिथं टॉर्क प्रोड्यूस होणार आहे आणि हा टॉर्क कुणाला प्रोपोर्शनल असणार आहे, तर आमच्या या ठिकाणी थीटाला, थीटा मीन्स अँग्युलर डिस्प्लेसमेंटला, आणि त्यांच्या दोघांच्या डायरेक्शन म्हणजे कोणाच्या, टॉर्क्यूची आणि इथं असणारे अँग्युलर डिस्प्लेसमेंट, दीज आर अपोजिट टू इच अदर, आणि हेच वी हॅव टू रिटर्न हियर टो इज directly proportional to minus theta, or we have to taken here tau is equal to minus c theta, where this c is called constant, and this constant is known as a restoring torque. Restoring torque per unit displacement. Restoring torque per unit displacement means here angular displacement. Tau is equal to I alpha, where I be the moment of inertia, alpha be the angular acceleration. Then this is equation number 2. If we are to comparing these two equations, that is tau is equal to minus c theta and tau is equal to I alpha, we have to see that this I alpha is equal to minus c theta. That is on this both side we have to see that is in left side tau is the same term, therefore this RHS also equal, therefore we have to return here I alpha is equal to minus c theta. We have to calculate for the angular S.H.M of the body, the restoring torque acting upon it for angular displacement theta, that is tau is directly proportional to minus theta. Hence for we have to taken tau is equal to minus c theta, that is this, where this c is called as a constant. This constant is known as a restoring torque per unit angular displacement. We know that is the I is the moment of inertia of a body, then torque acting on the body is given by tau is equal to I alpha, where alpha is the angular acceleration, that is we have to get the value tau is equal to I alpha. When we have to see that here we have taken the value for tau is equal to minus c theta, and here we have to get the value for tau is equal to I alpha. When we have to comparing these two equations, we see that this left side are equal, therefore this RHS also equal, therefore we have to return here, hence I alpha is equal to minus c theta. We have to get the value for this alpha in case of the angular displacement, then we have to know that alpha is equal to d square theta upon a dt square. This value we have to substitute in this equation, then equation becomes I d square theta upon dt square is equal to minus c theta. Hence we have to written here I d square theta upon dt square. This minus c theta we have to taken on the left side, plus c theta is equal to 0. This is the equation for differential equation for a angular S.H.M, that is I d square theta upon dt square plus c theta is equal to 0. If we have to divide by this I on both sides, we have to get the value d square theta upon dt square plus c theta upon I is equal to 0. Hence next step d2 theta upon dt square is equal to, when we have to taken the c theta upon I term on the right side, we have to get the value minus c theta upon I. This d square theta upon dt square means कौन है alpha, alpha means angular acceleration, hence here we have to return alpha is equal to minus c theta upon I. We know that is c be the constant that is a constant restoring torque per unit angular displacement. That's C I R constant. If C and I are constant, then we have to written here alpha is directly proportional to minus theta. Alpha, that is the angular acceleration, that is this angular acceleration is, that is this angular acceleration is directly proportional to minus theta. Means angular S.H.M is defined as the oscillatory motion of a body in which the torque or angular acceleration is directly proportional to the angular displacement and its direction is opposite to that of the angular displacement. Means काय सांगणार इथं, this is a alpha or this is a काय सांगितलं होतं त्या ठिकाणी torque. This torque or काय म्हटलंय त्या ठिकाणचं angular acceleration is directly proportional to the, this theta with the angular displacement is directly proportional to the angular displacement and its direction that is, here we have to take on the minus sign, here also we have to see the minus sign. This minus sign indicates that this angular acceleration or torque is opposite to that of the angular displacement, and this is the definition for the angular S.H.M. That is, angular S.H.M is defined as the oscillatory motion of a body in which torque or angular acceleration is directly proportional to the angular displacement and its direction is opposite to that of the काय सांगितलं त्या ठिकाणी angular displacement. 2 pi upon omega. Hence T is equal to 2 pi upon, in case of linear S.H.M, in case of a simple pendulum, we have to see the formula for the period of simple pendulum. T is equal to 2 pi upon omega, and for this omega we have to written here acceleration per unit displacement. And in case of angular S.H.M, we have to see the period of angular S.H.M. It is given by T is equal to 2 pi in the root angular acceleration per unit angular displacement. And this is the formula for time period of a angular S.H.M. That is, T is equal to 2 pi upon in the root angular acceleration per unit angular displacement. Magnet vibrating in uniform magnetic field. If a bar magnet, that is, this is a bar magnet, this bar magnet having the two poles, one pole it is a N, another it is a S. This is a bar magnet having a magnetic length that is a 2L. This bar magnet is freely suspended in uniform magnetic field. Here we have to see that this is a uniform magnetic field. If we have to place this bar magnet in uniformly magnetic field, that is the vector magnetic field which is denoted by the letter vector B, it remains in equilibrium position. Means it remains काय झाला, equilibrium position म्हणजे mean position ला with its axis parallel, कुणाला parallel आहे, parallel to that of the magnetic field. If it is given a small angular displacement, here we have to see that this is the equilibrium position of a bar magnet. If we have to release, if we have to twist it, this bar magnet through a small angle theta, that is, here we have to displace this bar magnet. This is the mean position or equilibrium position of a bar magnet. If we have to displace this bar magnet, then it making some displacement, that is the angular displacement theta about its an axis passing through its center and perpendicular to itself. We have to see that let mu be the, that is, here mu be the magnetic dipole moment. Let mu be the magnetic dipole moment and B is the magnetic field. Mu be the magnetic dipole moment and B is the magnetic field. In the deflected position, a restoring torque which is acting on the काय करणार आहे त्या ठिकाणी bar magnet. That is when we have to twisted this bar magnet, it becomes काय होणार आहे त्या ठिकाणी हा back into the काय होणार आहे त्या ठिकाणी mean position. That is this torque here, this restoring torque acting on this bar magnet. Here we have to see that is when restoring torque act on this body, the magnitude of this torque is given by tau is equal to minus mu b sin theta. We have to see that this theta, that is this angular displacement, is a very small. If theta is very small, then sin theta is nearly equal to theta. Theta is nearly equal to sin theta is nearly equal to theta. Then this equation becomes hence tau is equal to minus mu b theta. That is we have to get the equation tau is equal to minus mu b theta. When we have to take that is in case of only magnitude, we have to return tau is equal to mu b theta in case of the magnet. For clockwise angular displacement theta, the restoring torque it is in a anti-clockwise direction. Means काय होणार आहे, जर आमचा थीटा जर असेल क्लॉकवाइज डायरेक्शन मध्ये असेल तर आमचा रिस्टोरिंग टॉर्क कसा असणार आहे, अँग्युलर सॉरी इट इज इन द अँटी क्लॉकवाइज डायरेक्शन मध्ये असणार. लेट mu is the magnetic dipole moment and B is the magnetic field. If we have to release this bar magnet from this equilibrium position, this is the equilibrium position of a bar magnet. If we have to twist it, that is we have to taken some angular displacement, that is the theta. When we have to release this bar magnet, then it performs the angular S.H.M. That is, if this theta is in a clockwise direction, the torque acting on this bar magnet which is in a opposite direction. Hence, we have to written here when we have to written there, this torque and this angular displacement are oppositely directed. Therefore, we have to written here tau is equal to minus mu b sin theta. This angular displacement which is a very small, therefore we have to written here if theta is very small, then sin theta is nearly equal to theta. Hence equation becomes tau is equal to minus mb theta. From this equation we have to say that when this angular displacement is in a clockwise direction, then this torque which is in a anti-clockwise direction, means angular displacement ची डायरेक्शन क्लॉकवाइज मध्ये असेल तर हा रिस्टोरिंग टॉर्क जो आमचा आहे तर रिस्टोरिंग टॉर्क इट इज इन अ अँटी क्लॉकवाइज डायरेक्शन. मीन्स काय सांगितलं, दिस टॉर्क अँड दिस अँग्युलर डिस्प्लेसमेंट आर अपोजिटली डिरेक्टेड. In case of magnitude, we have to written here. In case of magnitude, we have to written here. That is, tau is equation between torque and angular acceleration. That is, tau is equal to I alpha, where tau be the torque, I be the moment of inertia, and alpha be the angular acceleration. When we have to comparing this equation 1 and equation 2, we get the value, that is I alpha is equal to minus mu b theta. Hence, we have to calculate the value for the angular acceleration, that is the alpha. Alpha is equal to minus mu b theta. This term I on the left side we have to take on the right side. Then we have to get the equation alpha is equal to minus mu b theta upon I. Then we have to see here this mu term, that is the magnetic dipole moment, it is the constant term. This b, that is the magnetic field, also it is a constant term. And this I, that is the moment of inertia, also the constant term. And this theta is the angular displacement. Then we have to say that as mu, b and I are a constant. If all these terms are constant, then we have to return that this alpha is directly proportional to minus theta. This alpha means the angular acceleration and this theta means the angular displacement. That is, from this equation we have to see that this angular acceleration is directly proportional to that of the angular displacement, and this angular acceleration and the angular displacement are oppositely directed. Then we have to find out the value for the angular acceleration per unit angular displacement. We have to take the, in case of magnitude, this angular acceleration per unit angular displacement, we have to get of the value mu b upon I in case of a magnitude, that is the angular acceleration per unit angular displacement. We magnet, the period of vibration of the magnet, which is equal to T is equal to 2 pi upon omega. Hence T is equal to 2 pi. We know the value for the omega, that is angular acceleration per unit angular displacement. Then hence T is equal to 2 pi. We have to get the value angular acceleration per unit angular displacement. This value we have to take here, that is we have to get the value, that is in the root mu b upon I, means we have to get the equation for is equal to 2 pi upon in the root mu b upon I, that is equal to 2 pi in the root I upon mu b. Magnet performs angular S.H.M. The period of vibrations of the magnet is given by, we have to get the value T is equal to 2 pi in the root I upon mu b, where mu be the magnetic dipole moment, b be the magnetic field, I be the moment of inertia,